Hello and welcome to week 5. In this lesson, we are going to look at search algorithm. My name is Mildred. So far, we have looked at the different sorting algorithms. We have looked at how they perform in terms of the time complexity and also the space complexity. And we have seen so far that no one algorithm is best than the other. It just depends on your use case. And so when you want to talk about the best sorting algorithm, you have to compare that with your use case. If you are dealing with large data, if you are dealing with small data sets and the likes. We want to look at the algorithm for searching, and the difference between search and sort algorithm is that sorting algorithms modify the array while the search algorithm leaves it unchanged. We use them to find specific elements, and that specific element is the target in a collection of data, and this collection of data will be either an array, a list, in a database, and so on. There are two fundamental searching algorithms. We have the linear search and the binary search. We have other specialized ones, but we're going to start with these two fundamental ones in this lesson. Now, the linear search is a sequential search. What it does is looks through the elements in an array one by one until it finds the match, and when it finds that match, it returns the index of the found elements, and if that element is not found, it looks through to the end and returns -1. So we want to implement the linear search algorithm in Python. It is the simplest search algorithm in linear search, and we'll pass in the array and the target that we are looking for in the array. So we'll say array, and the second parameter is the target. Now we say that it's for us to loop through that array from the beginning to the end, and then we return the index of the found element. So let's get the length of the array, and we'll say the length of array is stored in n. We want to loop through this. So for I in range, so we start from 0, so the range will start from 0, and n at n is always exclusive, so we can say for I in range n. Now we want to check that element is equal to the target. We want to return the index position. So we'll say if array I is equal to target, we want to return the index position I. But if it's not, we want to return -1 like this. So we want it to loop to the end and return -1 in the end if it doesn't find this target. Alright, so this is just a simple implementation. So you see how easy the linear search is to implement. So let's test and see. If name equal to main, so we want to say we have this array, let's get these numbers, and we want to set a target. Let's say the target is equal to 70, and let's say the result will now be equal to linear search, and then we pass the array and the target here. So let's say if the result, so we'll say if result is equal to -1, let's print search term not found or something like that. So if the result is equal to -1, element not, and if it's not, so we'll say else. So we can print the index position. So just say element found. So returning I. So let's say print element found at, let's say the element found at result. So get the index position. And so when we run this, we see element found at index position 3. Alright, so 70, 0, 1, 2, 3. So we'll see the index position. When we change the target from 70 to like 90 and it doesn't exist, you say element not found. So this is the linear search implementation. The time complexity will be something like, the best case would be if the item is found at the beginning, or the element is found at the beginning, and then it will be big O of 1, right? And the worst case would be if it is at the end or it is not found. So it has to go through all the items in the array, which is going to be n. The time complexity worst case will be n. And then the average case would be where if it's somewhere in the middle, which is also going to be n, which is just like n over 2n. And the space complexity is going to be 1 O of 1 because no extra space is used. So you can reason it out, and then you'll be able to think about what the time and space complexity might be. Now the advantage of this is that it's very simple to implement, as we can see, and we can use it for unsorted lists, and we don't need any additional data structures when we use it. The disadvantage is when the list is large, it becomes very slow because it has to check each element, and it's not as efficient if we compare it to other search algorithms. And so let's look at the binary search and see how efficient that will be compared to the linear search. Now the binary search is different from the linear search. It is an algorithm that works only on sorted lists, and what it does is that it repeatedly divides the array into half and keeps searching them. Continue dividing it into half and searching from the middle and until it finds the item. So when it sorted and it divides it into half. If the target is less than that middle element, it searches the left. If it is greater, it searches the right. You continue to repeat this half division until the element is found or the range is empty. So let's see how we can do that repetitive search for binary search. So let me put this as binary and I'll change this to the binary search. So we said the algorithm is to get the middle item, and then if the target is less than the middle, we want to search the left. If it is greater, we want to search the right. And so let's say, but you know, when you are working in production, you do all your checks to see if the array is sorted. If it is not sorted, you want to sort it first. It only works on sorted array. So for the purpose of this lesson, we'll just assume that the array that is passed in is sorted, or you can just use the sort function in Python to sort your array. So you always want to make sure that the array is sorted first before you move on with binary search. And if it's not sorted, you say maybe raise an exception or raise an error and say the array is not sorted, and then you try to sort. So let's get this length of the array. We store it in n, and we want to say let's get the left part, the right part, and let's initialize the value of it. So let's say left, let's name this left, we'll say right. So there are two ways that we can actually do this. We can do it in an iterative way and we can do it in a recursive way. So I'll try both so we can see. So iteratively, we'll do it like this. Let's say left and right will now be equal to, let's say left and right is equal to 0, and so left will be 0 and left right. So we're looking at the two ends of the array. The left end will be 0 and the right end will be the length of the array minus 1, so it will be n minus 1. So we're getting the first index position and the last index position. Okay, so the right is n minus 1. Now we want to maybe loop through and say if left is, as long as left is less than or equal to right, we want to get the middle to be, we'll divide by 2 to get the middle. So let's do it like this. We want to avoid potential overflow, so we'll say, let's use the while loop. While left, right, is less than or equal to right. So while left is less than or equal to right, we want to say the midpoint will now be equal to left plus, so let's say right minus left divided by 2. Let's round to the nearest digit. Okay, so the midpoint is going to be left plus right minus left divided by 2. There are many ways you can do this, so I'm using this like this. All right, so the left is 0 plus this. Why? Because I want to do it iteratively, so that's why I'm writing my midpoint like this. So if array, so if the item at the midpoint is equal to the target, we want to return the midpoint. Okay, but if not, so we can use elif because we have 3 conditions. But if it is less than, we want to repeat that division on the left, right? So say if it is less than target, we want to say left is equal to midpoint plus 1. Okay, and then else it's going to be the right, and then right will be equal to mid minus 1. And so if all of this condition is not met, we want to return minus 1. So you see what I'm trying to do here? I'm saying that it should check the length of the array. The left of the array is the first index position, the right is the last index position. If the array at the midpoint is greater than the target, you want to shift backwards. If it is less than the target, we want to move forward. Okay? So that's what it is. You can think about it in a different way, but let's test this and see. And let's say our target is 10, for instance. So we want to check this to see element not found, make our target 4, element found at 3. All right, so we have this working, and this is like the iterative method that we use, but we can do this recursively. For the recursive, we have to pass the left and the right point when we define it. So let's say the binary search, let's try the recursive method, and let's say array target. So let's say we have the length of the array stored here, right? And we want to say if the left, let's have the left point. Let's say left is equal to 0 and then right is equal to n minus 1. If the left is greater than the right, okay, if left is greater than the right, we'll just return minus 1. That means the array is not found. So it has gotten to the end, there is nothing on the right, the left is greater, return minus 1. Now we want to get the midpoint. Let's get it exactly the same way we got it the last time. Left plus, let's say left plus right minus left over 2. And now we say if array, the midpoint is equal to the target, we want to return the midpoint as the found index. But if the midpoint is less than the target, we want to to return now recursively binary search, we'll say the array target. And when we want to do this recursively, we have to have, well, let's do it this way and see. I think that there's how I could pass this left and right as the argument here, and so left now becomes mid plus 1 and then right, and then when it comes to when the midpoint is greater than the target, then it becomes mid minus 1 and left. So let's try this first. Return binary search array. So let's run this. I think this will not be right, but let's see it. Alright, so when we run this, we have 4. So 5 is located at index position 4. Let's see when we put 8, and we do not have that coming out. So it says maximum recursion depth exceeded. So this is the problem that I was suspecting that we might have when we do this, because the way I have specified this to happen, so we are looking for 8. 8 is here. 0, 1, 2, 3, 4, 5, 6, 7, 8. We can get 8. We can get index position. We can get 9. Found that there. But see, we've got a problem here. If I put 3, we have more problem here because it's a recursion error. And if I come back to maybe 5, the midpoint, we'll get 4. If I come to 6, we get this. So you can see this error makes it easy for you to see the kind of implementations that are not right. So now let's say we pass the left here and the right here. And while we're working, we say we don't initialize the value of left and right because we want it to be automatic. So we say if left is greater than right, we want to return minus 1. And when we get the midpoint is equal to the target, return mid. If it is less than the target, we want to recursively call this. And now if it's less than the target, that means we are going mid plus 1, right? And then we are passing the right value. But if not, we are going to have the left and then we'll have mid minus 1, all right? And so this time it should work better. So we have missing 2 required position arguments, left and right on the, so the left will always be 0, and then the right is going to be the length of the array minus 1. So we'll say len array minus 1. And so when I run this, we get it correctly specified. So you can look at how we did this and try to reason why we had to do it this way, because we wanted to recursively divide the left and the right. We always want to set the new value for the left. Once the midpoint is less than the target, the midpoint plus 1 will now be the left. And if the midpoint is greater than the target, then midpoint minus 1 will now be the value for the right. And that's what we did here. So if you do it recursively, so you see the iterative method is easier to think about. So when we look at the time complexity of this, we know that the best case is always when the middle is a target. It just returns it immediately. So the time complexity is O of 1. The worst case will be log of n, which will require several divisions. And the average case is maybe we'll have log of n2 when we have halfway through the list. All right. So the recursive will take more time. It's always better to use the iterative method, because when you use recursive method, you will get the space complexity of log n due to the call stack, but the iterative one, the space complexity just remains 1. The advantage is that it's faster than the linear search, especially for large data sets. It reduces comparison significantly because the growth is logarithmic. It reduces comparison significantly and it works efficiently on sorted data. The disadvantage of this is the data always has to be sorted. It is more complex to implement than the linear search. So you can refer to your lesson resource and look at the side-by-side comparison of linear and binary search, and you want to know the situations in which we use each of the algorithms. So when you have small data sets that is unsorted, linear search is your go-to. If you have large data sets that is sorted, binary search. If you have to do frequent insertion removal, unsorted list, linear search. And when you have any static data with frequent searches, you want to use binary search. So in summary, the linear search works on unsorted data, binary search works on sorted data. Linear is easy, binary is not so, it's okay, but not as easy as linear. The time complexity for linear search is the length of the array ON, and for binary search is log n, and the space complexity is 1 for both. The technique for the linear search is sequential, and the binary search, you can see we are doing divide and conquer. And the efficiency for linear search for large lists is low, but the efficiency is high for large lists for binary search. So this is where we end this week's lesson. Thank you and see you next week.